Hey everybody, I'm Aaron. Welcome back to the channel. Well, as you can see, I'm in the 70s set, so that means we must be talking about something from the late 70s or early 80s, and indeed we are. So I'm doing a follow-up to a video I did earlier about the Atari 2600, where I covered 10 things you didn't know about the Atari 2600, or as I like to refer to it, the VCS. Now, if you haven't seen that video, I'd highly recommend that you go back and take a look at it. It's one of my most popular videos on the channel, and there's a lot of really cool trivia in there about the Atari VCS. So if you haven't seen it, go take a look and then watch this as a follow-up, because there'll be some points that you'll need to know from that first video, which will make this video make a lot more sense. But this video is 10 technical things that you didn't know about the Atari 2600. And just like in my previous video, you're going to be hearing from some of the people that brought this system to life. That's right, you're going to be hearing from some of the engineers who worked on the hardware and the games as we go through, so you can get it straight from the horse's mouth. Okay, I'm sure some of you know some of the things I'm going to be talking about today, but I bet there's one or two things in here that you didn't know. There's at least one thing in here that I didn't know when I recorded that original video. So, armed with my trusty heavy sixer at my side here, I'm ready to dig into this list. By the way, did you know why it's called a heavy sixer? Ah, crap, that one's not on my list. Well, I do have a few bonus facts at the end. I guess I'll add that one too. So stay tuned till the end and find out the answer to that one, as well as a few more. So it's 10 technical things you didn't know about the Atari 2600 or VCS, and it's coming up right now on the Retro Hack Shack. The Atari VCS only had 128 bytes of internal memory, and the ROM cartridges at the time only had between 2 and 4K of memory built into each of them. Now, I know I mentioned this on my earlier video, but I'm going to be going into a little bit more detail this time, and it's critical to understand just how small 128 bytes is so that you can appreciate some of the things that are coming up on my list a little bit later. But to start with, actually the original spec for the system called for only 64 bytes of memory, which is unbelievable, but it was because memory was such a premium back in the day. But let's take a look at just how small 128 bytes actually is. Here's a single frame from one of my recent videos. It's 3,840 pixels wide by 2,160 pixels tall. It's 11 megabytes in size, and that's just a single frame. 60 frames a second, 4K video is no joke. And here's what it looks like when I shrink it down to 128 bytes. Can't see it anymore? Well, that's because it's only 5 pixels high and 5 pixels wide now. I also had to save it as a raw image, surprisingly. Usually you would apply compression to get the image size smaller, but this file is so small that adding compression actually makes the file size bigger because of the metadata that needs to be added to the file to make the compression work. To illustrate this another way, if you're on Windows, you can open up the venerable Notepad application that's been around forever and start typing characters. By the time you get to your 128th character on the screen, that represents a file that's 128 bytes in size. Each character you type is about 1 byte in file size. So that's it. You get one line of text here and you're already at 128 bytes. Not only that, but trying to squeeze your source code down to fit on a 2K ROM cartridge is just incredibly difficult. Listen to how some of the developers used to deal with the problem of having their source code be just a little bit too big to fit into that 2K ROM cartridge.
Programmers today don't understand this tremendous pressure to shave 1 or 2 or 3 bytes out of their source code just to fit into the 2K boundary. I usually, at the end of my cards, when I was squeezing bytes, which was really painful, I'd usually go home, have a couple beers or a couple glasses of wine. It caused me to look at my code entirely differently. And I would find ways that were non-obvious to save bytes. Of course, I'd wake up the next morning and half of them were ludicrous because they're just buggy as hell. But that was the way I shrunk code at the end.
I mean, the kinds of things that we would do. Normally when you're writing a piece of code, you will initialize your registers and execute the algorithm that you're creating. But if it happened that one of the registers from the previous routine happened to have a 7 in it, you would figure out how to write your algorithm so that it took advantage of the fact that there was already a 7 in the register so that you could save the 2 bytes necessary to load the register with the value. We would have tables, graphic tables. We might make a slight change to the graphics so that the last byte of the graphics table is the same as the first byte of the next picture. If you ever had to go back and look at that code again, you would have long since forgotten that you were relying on the fact that there was a 7 in the register from the previous time this routine was called. And the tricks that we were pulling just to save those bytes were truly insane.
With so little RAM and so little storage space on the cartridges, programmers had to get really clever in their usage of those resources to make some really impressive games. Racing the beam refers to the way that the Atari VCS drew its graphics on the screen. There were no bitmap graphics, so they had to draw out each pixel one at a time as the scan line traced across the CRT. In fact, of the over 200 scan lines in a single frame of video for the Atari VCS, just one of those scan lines equated to only 76 clock cycles on the CPU. Given that you needed to both read data from ROM and then write data to memory so it could be executed by the CPU, that left very little room for gameplay code in between. This also meant that you had to be sure to count every scan line and every clock cycle so you would know precisely when you had to change a color or move the position of a sprite on the screen. This would lead to other interesting quirks, as you'll see later on.
The Snowland environment was almost completely unique in the industry that I've been familiar with, in that the programmer has to pay attention to where the code is executing to the precision of a microsecond.
Right?
Recycle.
Count every cycle.
No, it was a microsecond because that was a cycle.
What,
840 nanoseconds.
Exactly.
840 nanoseconds?
And that was 3 clocks, 3 visible clocks
Right.
per cycle. So with that particular object, I had to have 3 clocks of slack. I had to make sure that those writes were occurring not just anywhere in between. It had to be so that I had 3 clocks on either side, so that I could tick the thing forward 3 clocks before advancing the kernel by a cycle.
If you want to get really technical about how racing the beam works, Retro Game Mechanics Explained did an in-depth explanation of how it works, and I will leave a link to that video below. Now that you can see some of the challenges that the programmers of the VCS were up against, it's a little easier to understand some of the nuances that we all may have noticed as kids playing games on the Atari. For example, in Pac-Man, the ghosts flicker because there weren't enough sprites to handle all 4 ghosts separately. So the game shared one sprite for the other 3 ghosts instead. How did that work? Well, the first ghost was drawn on one video frame, and then the second ghost was drawn on the next, and so on. This meant that each ghost was only visible a quarter of the time. Luckily, there are 30 frames per second, so you don't notice it too much, and your brain fills in some of the missing details. In other games, they use a technique called Venetian blinds. Chess is a good example of this. By shifting the graphics up for every other piece, it left more cycles to process code. Also, while the computer player was thinking, the screen would go blank and flash. That was because the game needed more resources to process code, so it had to stop processing the video signal momentarily while it did that. The flashing was due to whatever bits happened to be left in the video registers at that particular moment.
And then Bob Whitehead came out and he did some experiments, and we came up, because of these 8-bit graphics objects, one of them, 2 8-bit graphics objects, we realized that how are we going to display the whole chess pieces, which would require 8 graphics objects instead of 2. At the same time, I believe the processor had to load them on the fly. So, do you remember, Larry, how this Venetian blind effect?
Venetian blind. So this is players. If you recall, we talked about earlier, and you can see that this pawn, for instance, is down a line, and this pawn is down a line, and this pawn is down a line from this pawn. So it's Venetian blind because every other line, player 0 is used here, here, and here. The next line here, here, and here. And then overriding the register to move it over to here. And so Bob Whitehead, and we call this the Venetian blinds, it looks like Venetian blinds. And he invented this purely out of the air. So now the computer's thinking, and now it's come back and it's moved its piece.
Related to these two things are the black lines that appear on the left side of the screen in some games, like Air-Sea Battle, Space Invaders, and many others. This is a result of trying to update the position of multiple sprites in the middle of drawing one frame of video. It turns out that one way to do this was to call a command named hmove, which had the effect of delaying the horizontal blanking by 8 clocks. After the delay, the normally invisible horizontal blanking signal would continue, but now it would be offset onto the visible part of the screen. Later games would fix this by just blacking out that whole side of the screen, so the user wouldn't even notice it.
You know, the original design, no one ever thought of changing the player during the screen. And that's, in fact, the result is this stair-stepping problem.
Yeah, here's the way it worked. We had, from coin-op, being cheap, we had polynomial counter-based horizontal positioning. And it was kind of clunky, but it worked. And then the programmers came along and they said, can't we just write a binary position on the screen? And it would have cost a bunch more chip area. So I wrote this little routine that you passed it a binary address, it figured out what loop count to wait during the screen to issue a reset to the counter, and then what horizontal delta to add to it to get it to be exactly to the pixel address where it should be. A side effect of that routine was, A, we didn't have to change the hardware, so it was cheaper, so it yielded better. But it meant that you had to run this routine if you wanted to reposition the sprite on the fly. And if you look at that display, those sprites are being repositioned on the fly. And every time that happens, because of a bug in the hardware, it draws that little bar on the edge of the screen.
Did you ever wonder why when you hit the tanks in combat, sometimes they would bounce through the walls and appear on the other side? Well, it turns out that was a bug in combat that the engineers consciously left in the game because it would take more time and code to fix that particular bug in the game than it would just to leave it alone and make it into a feature. And sometimes these features would end up being the most fun parts of those games.
Oh, there you are. It was Larry's innovation to have everybody bounce through walls.
No, that was after. No, what Al told us is if there was a bug or a perception of a malperformance, you turn it into a feature.
Yeah.
Yes.
You got it for free,
That's what
so you can't fix it.
So what happened is due to all the reflections, remember this a quadrant, I'm sure you discussed the quadrant reflecting. Somehow it was a bug because it would take extra programming to stop it from reflecting, so we just let it stay.
After I learned how to program and started looking back at some of the Atari games that I loved as a kid, like Pitfall and River Raid, I couldn't understand how they could pack so much information into those cartridges so that the levels on those games or the screens on those games would be repeatable time after time. Every time you reset the game, the order of those screens was exactly the same. In order to do this, another trick was developed. Programmers like David Crane figured out how to use a pseudo-random number that would spit out the same series of digits every time the game was started. Programmers could then use that number to represent the various elements on the screen. So instead of having to hard code every element on every screen, you could just use that pseudo-random number and save yourself a ton of space, both on storage and memory.
Well, I wrote a polynomial counter that was reversible. What that means is if you incremented it, it would go from, say, 12 to 93 in the pseudo-random sequence. And then if you decremented it, it could go back from 93 back to 12, which was kind of tricky. It was hard to do, but once I did it, I said, well, this is great. All I have to do is when Pitfall Harry runs off the right side of the screen, I increment it. And then when he runs off the left side of the screen, I decrement it. And now I've got a sequence of numbers that are 255 long in sequence, and it makes this circular world, and it's always repeatable. So then I take that 8-bit polynomial counter, and I take 3 bits of it for the path object, 3 bits of it for the shape of the middle, whether it's 1 hole, 2 holes, water, tar with or without a vine, that sort of thing, and make 4 different tree patterns so that when you moved across the screen, the trees changed a little bit, so it told your mind that, gee, I must be on a different screen because the trees moved. And where the brick walls are in the underground passage and that sort of thing. So the polynomial counter itself was about, 16, 17 bytes to generate. And then from that, I chose different graphic elements for the world, such as for that area in the middle, I decided, 1 hole with a ladder, 2 holes or 3 holes with a ladder, and the various ponds, pits, or tar pits, plus whether or not they had alligators in them, whether or not they expanded and contracted, which we ended up calling quicksand, and in fact whether they had a vine over them to allow you to swing across.
Some of the early Atari games like Air and Sea Battle here, Combat, and Street Racer suddenly end after 2 minutes and 16 seconds exactly. But why is that? Setting a time limit on a particular game was a conscious choice by the programmer, and 2 minutes was known to be a good limit in the old arcade games to avoid the player getting bored or losing attention. The reason it's exactly 2 minutes and 16 seconds is that in order to save coding space, it was easier to use a binary counter of 2, which you could increment every 60 frames. When the counter reached 2 to the power of 13, or 8,192, the game would end. 8,192 frames divided by 60 frames per second when you account for interlacing equals 136.5 seconds, or roughly 2 minutes and 16 seconds. If they had used 2 to the power of 12, the game would have ended after just 1 minute and 8 seconds, which is too short, and 2 to the power of 14, the game would have ended at 4 minutes and 32 seconds, which at the time was deemed too long. So 2 to the power of 13 it was, and that's the closest to 2 minutes they could come by doing it this way. The original design of the Atari VCS called for 2 speakers to be mounted inside the case to be used for the game sound instead of using the speaker in the TV. If this sound design had made it into production, you probably would have heard the left player having his or her sound effects coming from the left speaker, and the same type of thing for the right. Even though this design was changed late in production, the molds for the plastic weren't updated to reflect this, so the early models of the Atari VCS have mounting brackets and slots where the speakers were supposed to go. 2 independent sound generators remained built into the system, even though they changed the sound design. There are some games that take advantage of these 2 sound generators, and I'll be posting a follow-up video showing how you can mod your system so that you can hear what it would have sounded like to have 2 independent speakers inside the chassis. Be sure to subscribe and hit the bell icon to be notified when that video hits the channel. Unlike the Atari VCS, many computers that came out around the same time had the ability to load programs from cassette. The holy trinity of home computers that came out the same year as the Atari VCS in 1977 were the Apple II, the Commodore PET, and the TRS-80. All of them supported loading programs from tape, as floppy disk drives were very expensive at the time. However, the Atari VCS used cartridges and didn't have a cassette interface. I'm not sure if this was ever considered in the design phase, but it probably would have been deemed too expensive to add the extra components. As I mentioned in my first 10 Things video, Atari was really building this thing to a low target price point. However, loading from cassette tapes was made possible in 1982 by using the Star Path Supercharger. 1982? Yeah, probably bad timing considering the video game crash of 1983, and it also probably explains why I only found out about the Star Path Supercharger recently from a friend of mine. This cartridge adapter not only allowed for loading games from cassette tapes, but also added a whopping 6 kilobytes of additional RAM, which allowed for some pretty impressive games to be written for the system, although they're not all as good as you might think. I'll be doing a dedicated video about the StarPath Supercharger in an upcoming episode, so remember, subscribe, bell, and you'll be able to see it. The Atari VCS didn't ship with a built-in pause button or switch. This led to some pretty frustrating moments as kids when our bladders filled up and we had to make a mad dash for the bathroom while we handed the controllers off to a friend or a sibling, and hopefully they could keep the game going long enough for us to get done in the bathroom and come back and pick up where they were at. However, there were some games that made use of the physical switches on the console to pause the game, even though the switches weren't meant for that originally. For example, a number of games like Super Cobra used the black and white color switch on the console to pause the game. Burger Time actually used the left difficulty switch to be able to pause the game. You can also add a mod to pause any game. It uses the timing on the TIA chip to signal the 6507 processor at just the right time to effectively halt and pause the processor until you take that pause control off. I'll be making a video on installing the pause mod in an upcoming video, so yep, subscribe, bell, it's getting old now. As children, the more musically inclined among you may have noticed that the music coming out of your favorite games for the Atari VCS was always just a little bit off. Why was that music always a little bit flat or a little bit sharp? Well, it turns out that in order to generate the right note, the system had to be able to generate the right frequency of that note. In order to obtain the right frequency with the hardware that's inside the VCS, the system engineers needed to split up the clock frequency into smaller parts. Unfortunately, because of math and the limitations of the system, they weren't able to match up exactly the right frequency to get each note just right.
The counters that we used for the sound had a limited resolution in how you could divide the clock, so we couldn't actually hit all the frequencies that you need for music to have the full, they called it a top octave counter to get it just right. So, but we said, you know, people that really play games will put up with kind of music, so we had something like a musical scale, and later on.
440, we ended up with like 438.5. And the next, you know, a B should have been like, 503, and we ended up with like 492. And generally it was flat.
Yeah.
Occasionally it was sharp, but we try to pick the frequency closest to the tone. And so the music was always a little bit off, but they gave it a totally unique sound. And to this day, everyone knows that sound.
The first Pitfall was an amazing game when it came out, and by chance we were lucky enough to see a young Jack Black in the commercial for the game.
Just last night, I was lost in the jungle with Pitfall Harry, surrounded by giant scorpions and man-eating crocodiles.
David Crane came up with some amazing ways to get this game to look and play so well. When he started thinking of a sequel, he really pulled out all the stops. He built a patented circuit that was installed inside the cartridge to add music, flying creatures, vertical levels, and the ability to swim in the game.
Well, I exceeded the capability of the 2600 a few times, and actually the fact that certain address lines weren't out there and certain signals weren't out there were actually a challenge to figure out how to exceed that capabilities of the 2600. And what we did then was start to expand the capabilities of the 2600 by putting extra circuitry in the cartridge. I've also done cartridge with custom integrated circuit in it to improve video throughput, audio capability, that sort of thing. We really started to get carried away right near the end of the 2600's life. On the surface, it doesn't look like it's much different, but in fact, there are registers in the cartridge which are feeding data to the 2600 in almost a DMA fashion. There are 3 channels of audio being generated asynchronously, independent of the 2600, in the cartridge, and that information is being taken from the ROM as it's changing. A single address in the ROM is changing with audio data, and that audio data is then captured and output to the audio volume register. I'm actually doing a DMA on the volume to make that music. And it was reading through a sequence of images, a sequence of graphics, and computing the zeros above and below so that it could be positioned vertically on the screen. All that was happening automatically in the cartridge so that you could use more time in the kernel to display more objects. So it allowed you the ability of having more movable objects on the screen at any one given time. It saved a lot of calculation in the software and gave that ability through the hardware.
The chip in the cartridge was called the DPC, or Display Processor Chip, which, not coincidentally, was also the initials in David P. Crane's name. Okay, and last but not least, the bonus question that I threw in at the beginning without realizing I was going to do it. Why is the Heavy Sixer called a Heavy Sixer? Well, the first thing refers to the sixer part of the term, and that refers to the fact that it has 6 buttons across the top of the console. Later systems, even the ones that kept the wood grain design, moved the difficulty switches to little switches on the back of the unit and only had 4 switches. But the Heavy Sixer, as the name implies, has 6 switchers. But that's not the only thing, because there were later revisions that weren't Heavy Sixers that also had 6 switches. The other thing that's different is also in the very front of the name. The heavy part of the Heavy Sixer refers to the fact that this console is noticeably heavier than future consoles when they came out. This has a very much thicker plastic base underneath the bottom part of the console, and it is noticeable when you pick this thing up that it is heavier. This console also has a thicker bezel all the way, especially on the top here, and then around the front. And you'll also notice that around the front, it has this curved shape, this gradually curved shape on the front. When you see that curved shape and the thick bezel, there's a good chance that you're looking at a Heavy Sixer. Another clue is that the Heavy Sixers were made in Sunnyvale, California. Now, some of the other 6-switch models were also made in Sunnyvale, or at least they have stickers on the bottom that say they were made in Sunnyvale. But again, it's a clue. If you look at the bottom, it says it's made in Sunnyvale, has some of the other distinguishing features that I mentioned, then it's a good chance it's a Heavy Sixer. Last but not least, the Atari joysticks and the console all had kind of an orange paint around them, around the bezel here that went around the switches. There was an orange color, and of course on all the joysticks there was an orange paint on this grid that went around the joysticks. Well, on the Heavy Sixer, that wasn't quite so orange. It was almost more of a dark yellow. Now, at this point, a lot of the paint on these has faded off, so it's difficult to tell. But to my eye, even looking over here, the print on the various switches and the remnants of the paint that went around those switches on the bezel here is noticeably lighter in color than the paint that would have been on the later joysticks or the later versions of the console. So those are all the differences that I'm aware of for the Heavy Sixer. If you know of a few more, please leave them in the comments below. If you know of some more fun technical facts that you want to share with me and the rest of the community, put those down in the comments below as well. On my last video, I got a ton of extra comments and fun things to look up, and some of those things that were in those comments made its way into this video. So with that, I want to thank all my patrons for supporting the channel. Your support means a lot to me, and those names will be coming up in just a minute in the credits for this episode. So I hope you learned something new about the Atari VCS or 2600, and until next time, thanks for watching. Patrons receive ad-free and early access to content after the episode commentary, and of course, your name in the credits. If you liked that episode, here's a few more you might enjoy, and I thank you for your support.
End of line.